Okay, we left off on the last video talking about using rectangles to approximate the area under a curve. So there are three main rectangle approximation methods. There is the left-hand rectangle approximation method, the midpoint rectangle approximation method, and the right-hand rectangle approximation method. So the RAM stands for rectangle approximation method. L is left hand, M is midpoint, R is right hand. These just are different ways to draw the rectangles under the curve, and they give you varying errors. For instance, for the curve that we're going to look at first, f of x equals x squared, the left hand rectangle approximation is going to be an underestimation, while the right hand is going to be an overestimation, and the midpoint is going to be somewhere in between. So what do we mean by that? Well, we're actually going to literally draw rectangles underneath the curve and find their areas so that we can approximate the area under the curve. I'm going to go back to the Inspire here for a minute. So I've got a little program up here that came from Texas Instruments, and up here is the L, the M, and the R, so I can move this dot here over to M and R when we need it in a second. So my interval is from A to B, which is from 0 to 3. So I'm going to be finding the area under the curve x squared from 0 to 3, and I want to use 3 subintervals. So if my interval is from 0 to 3, and I want 3 subintervals, so that's 3 subintervals. And I have a mouse again, so sorry about that. 3 subintervals from okay, so that means I'm just going to subdivide my interval 3 times. It's very easy with this because it's just going to be a rectangle with a width or a length of 1. So if you look down here, I've already got it set up. My n is 3, so it's the number of rectangles, the number of subdivisions that I want. I'm using left-hand method, and my interval is from 0 to 3. So if you look here, the first rectangle looks like it's non-existent, and that's right, because if I were to draw this rectangle, and the left-hand approximation method is where I start on the left side of my interval. So since my interval starts at 0, my LRAM first rectangle starts at 0 as well. Okay, so I would literally put a point there, and it's at 0, so it's not going to have any height to it. So it has a 0 height and a width of 1. All right, my second rectangle is going to be at 1. So this is 1. So I'm going to start it right at 1 and draw it over here. And this is at 2. And this is my last rectangle. Okay, so I drew my rectangles. All right, remember we're finding the area under a curve, and over here it kind of gives it away. My LRAM for this one is 5, but the exact area under this curve from 0 to 3 is 9. Notice we're underestimated by quite a bit, by 4, because of this whole big space that we're not accounting for, because these rectangles are just a little too chunky. But we'll talk about what this means. So we drew 3 rectangles, right? How do I know? I know each width is 1, because when I subdivide from 0 to 3 3 times, I get rectangles with a common width of 1. So that's easy. I know every rectangle I'm going to do has a width of 1. That's great. So let's go back to our whiteboard here. So my left-hand rectangle, I would like you to draw those rectangles in here. Okay? And what we're going to do is do the calculation. So rectangle number 1, and I'll just abbreviate rectangle number 1, all right, has height f of 0, right, because it starts at 0, all right, and it gets multiplied by our width. So that's the height. And writing with the mouse is very tricky. So there is our common width. Remember, every rectangle, I was going to say common width, but I'll just put width. Okay, so my first rectangle has a height f of 0 times 1, which is the width. Well, I know f of 0 is 0. So that's going to be 0 times 1. So that rectangle is 0. Rectangle number 2. Well, I know that's going to happen at f of 1. That's my height. Or my length, right? Because if we're talking about rectangles, we're talking about length times width, right? Times 1. That's my common width. So f of 1, how high is that? Is that rectangle right here at 1? How high is that? Well, I just plug in 1. So my function's x squared. I plug in 1. So 1 squared is 1. So my rectangle number 2 is 1. And rectangle number 3, okay, is at 2 with a common width of 1. Well, f of 2, 2 squared, is 4. So 4 times 1 is 4. And remember, we split it up into 3 rectangles, right? All right, well, this rectangle didn't have any height to it. All right, so that ended up being 1, 4. So the total area was 5. And that's where that computer program got the LRAM of 5 here. Notice we're way off because the rectangles aren't capturing all of the area under that curve yet. And so I would take. So I'm going to write this a little better. It's all scrambled up here. But what this really was 3 rectangles. So I'm going to kind of write above. Oops. R1, R2, and R3, so you can see where they're coming from. Okay, and this was, okay, the rectangle with height f of 0 times our common width of 1 plus our rectangle with a height of 1. Remember, this is our left-hand rectangle approximation method with a common width of 1. And our third one that began at f2 with a common width of 1. Alright, so we had 3 rectangles. Alright, so that's our subdivided. We started at the left of our interval, so that's 0. And we did our 3 rectangles. And our common width was 1. Alright, so we literally would just find f of that value, make sure whatever that is. So this was 0, this one was 1, and this one was 2 or 4. And we add them together just like we did here. Notice we have a common width in there, right? So if we were to, we could sort of extract that 1. Alright, so it's not going to make much of a difference here. But when you have a common rectangle width, let's say you use 6 rectangles. So each rectangle width would be 1/2. Alright, well, instead of multiplying everything by that rectangle width, notice we could just factor out that 1. So we would literally have our rectangle width on the outside with our rectangle heights. And I'm going to sort of slant this down this way so I don't run into the toolbar there. So that where this is my common width. So notice the rectangle, then it becomes a lot easier. All you got to do is find the heights of each of those rectangles, multiply it by the common width, and you have all those rectangles, areas added up, and you have your approximate area under the curve. Alright, so I've shown you the calculation for the left hand. Let's look at the right hand. Alright, let's clear that. Okay, so I'm going to move this over to the right hand. Notice these rectangles are now over approximated. Well, because now my interval, remember, was from, whoops, let's move that hand out of the way. My interval was from 0 to 3. So, alright, 0 to 3. If I want a right hand approximation, I'm going to start on the right. So right hand quite literally means start on the right. Alright. So we're gonna start at the right hand side of our interval, right at 3. So that height right there is f of 3. This height, alright, going this way, that height is f of 2. And this height, going this way, is f of 1. So now, instead of our 3 heights being at 0, 1, and 2, we're starting on the right. So on the very right side of our interval, we're dividing it into 3 pieces again. We start with 3, so f of 3 with the width of 1, f of 2 with the common width of 1, and f of 1. So there's our 3 right-hand rectangles. And you would literally do the same thing. So if we look back over here, we would take it, I'll use green to just highlight that. So rectangle 1 for our right ram here would be, it would start out being f of 1, and then f of 2, and then f of 3. So our rectangles would be quite over. If you look here, it says our ram here is 14, because now we have this amount over, right? Okay, and you can probably now kind of get the idea of what you're going to be doing for midpoint, and make sure along the way you've been filling in all the blanks and all the notes so that you can refer back to this when you need to, so you can do the next set of problems or whatever's coming up. So let's go to the midpoint real quick before I end this one. Where is it on the right here? So midpoint, and notice the rectangles. The height of the rectangle is at the mid part of that interval. All right, so a little tricky to see, but instead of starting on the left or starting on the right, we start in the middle.
At this time, NCTET.
Recording at school is always a dangerous endeavor. Okay, so we actually start in the middle. We've divided this into 3 rectangles, and instead of starting at the very right or left, we're going to start in the middle. So right here is the height of our rectangle, and that is at f of 2.5. This one is in between 1 and 2, so that's going to be at f of 1.5. And here is in between 0 and 1, so that height is at f of 0. That is a 0, not a 1. 0.5. With still a common width of 1. Now, last thing I want to point out, look at our MRAM here. When it was a right hand, we're over by a lot. With left hand, you're under by a lot, just for this function. And for other functions that are shaped similar to this. But our midpoint, we're very close. And if you notice with our midpoint, we're going have some over approximation, but in the same rectangle we have some under approximation. And it looks like those are kind of equal. So with our midpoint rectangle approximation, we get some over and under in the same rectangles, which sort of end up helping offset each other. So our midpoints are going to be a lot closer because within the same rectangle you've got sometimes some equaling out there of the over and under. Okay, so that is all for the midpoint left hand and right hand. Make sure you're filling out all the things that are going with that, and we'll do a couple examples and move on.